Welcome everybody to Integrated Math 3. In today's episode, we're going to be discussing chapter 9.1.7, which is the tangent function. So before we jump into any kind of functionality of tangent, let's talk about what tangent actually is. So tangent of, say, some angle theta was always the opposite side over the adjacent side. So hopefully that brings us back to a little bit of integrated 2. And in this diagram, hopefully it would make sense that tangent of this specific theta right here would be y over x. And we saw that in integrated 2. We've seen that a couple times in integrated 3. But let's talk about what the roles of y and x actually are. Because y, if we were to look at the unit circle in that context, because remember, the unit circle is really just a graphic organizer that comprises all the special right triangles, and the unit circle really is just a circle with the radius of 1. So in this case, r would be equal to 1. The y would be whatever that y value was at that moment in time, dependent on the angle. And then x would be whatever it was. Now, remember, in this context, again, tangent of theta still equals y over x, so that doesn't change. But let's talk about this in a different kind of way. We know that sine of theta is equal to y over 1, which meant sine of theta is equal to y. Cosine of theta equaled x over 1, which meant cosine of theta equaled x. So hopefully it makes sense that if I just do a little bit of a substitution here, that y I could call sine theta. That x I could call him cosine theta. So another way of looking at tangent would be sine theta over cosine theta. Hopefully that makes sense. So there are two ways to look at tangent, and that would be these two ways. Or technically three ways to look at tangent if you include this guy, but they all ultimately end up being the same thing. So hopefully that makes sense in terms of what tangent actually is. Let's go ahead and we'll pop another unit circle, and then we will start dividing our y values by our x values. I'll be right back. Give me a second. And we are back. I actually just kind of copied and pasted a unit circle from Google into the document here. And we have a chart here, which is part of your resource page, which is all of your angles in, and we're going to go and ignore the angles in degrees for now, but we'll put down the angles in radians. And then we'll do sine and cosine, and then tangent, which is sine over cosine. So let's take a second. Let's just go and fill in the angles in radians here. So I'll go and switch colors here. This is going to be red. So this is 0. Our first known angle is pi over 6, pi over 4, pi over 3. 90 degrees is pi over 2. And I'll go and pause real quick and fill in the rest, and then we'll go from there. Give me a second. And here we are. So from here, hopefully you were able to pause and fill in all those radian values. Let's go and talk about what sine and cosine are. So what is sine? Well, sine of 0 is 0. Cosine of 0 is 1. Sine of pi over 6, I'm going to take the y coordinate. That's going to be 1/2. That's going to be rad 3 over 2. They're both going to be rad 2 over 2s for the pi over 4. And then the sine's going to be rad 3 over 2 for pi over 3, and 1/2 for cosine. Sine's going to be 1, and then cosine's going to be 0. I will pause now and fill in the rest of the sine and cosine. Please pause and do the same thing. I will see you in a few seconds. Okay, here we are. We have our radians, we have our sine of that value, a sine of that angle, and then our cosine of that angle. Now, tangent is sine over cosine. We talked about y up in this part of the video, so if you need to rewind and go back there, please feel free to do so. So now, let's talk about what happens when we literally divide sine into cosine. So I'll go ahead and scroll over here real quick. We have this table here. If I look at pi over 6, well, remember, the coordinates there are rad 3 over 2, comma 1/2. Now, I know it's reversed here. They put sine first, then cosine second. But here, remember, this is x, comma y. So I'm literally going to do 1/2 over rad 3 over 2. What that means is 1/2 divided by rad 3 over 2. And let's go and take us way back to elementary school when we learned that this would be 1/2 times 2 over rad 3. Those guys are going to cancel. You'll end up with 1 over rad 3, And now we've got to rationalize that denominator by multiplying the top and bottom by rad 3. We get rad 3 over 3. So that's going to be the first thing, rad 3 over 3. And I can't believe I always miss this one, the top one. The first one is actually radian 0. And the coordinates there are 1, 0. So y over x, or sine over cosine, is 0 divided by 1, which is 0. So sorry, I always miss those ones. I don't know why. The next one is going to be pi over 4. The coordinates there are rad 2 over 2, rad 2 over 2. So again, if I was to divide this out, it would be rad 2 over 2 divided by rad 2 over 2. Now for this one, I am not going to be doing this whole mumbo jumbo, because really what I have is something divided by its identical self, and anything divided by itself is always 1. So from here, now I'm going to go and do pi over 3. Well, what are the coordinates there? 1/2, rad 3 over 2. So if I did rad 3 over 2 divided by 1/2, I could see that as rad 3 over 2 divided by 1/2, which is rad 3 over 2 times 2 over 1. The 2's cancel. You're left with rad 3. And then from here, you're going to end up at pi over 2. I'm going to scroll down here real quick. Pi over 2. Your coordinates are 0, 1. So that means that y over x, right? Y over x, or sine over cosine, is going to be 1 divided by 0. And 1 divided by 0 is a very special kind of place, because that means that we are dealing with undefined. So hopefully you kind of already have an idea of what that graphical effect will look like when we have an undefined region of the graph. But I'm going to go ahead and have you guys pause. I'm going to pause also and fill in the rest. Just like sine and cosine, there's going to be those symmetric buddies. So you can go ahead and make the associations if you want, and then we'll be right back. And here we are with the rest of this table filled in with all of our values of tangent. And so I'm going to go ahead and delete this work right here. And then we're going to go ahead and graph a super detailed tangent. Give me a second. I will be right back with the graph. And here we are with our graph paper, and we're actually going to go ahead and graph this thing in blue, because I want us to pay attention to this blue section right here. We're going to be graphing these. So hopefully it makes sense that our input would be the angle and our output would be the side. So remember, these two boxes are the ones that we're paying attention to. In fact, you know what I'm going to do? I'm going to do this. Just so that we can ignore them, I'm going to go ahead and say, you know what? Goodbye. So here we are. We're going to be graphing this dude in blue. First thing to note, tangent of 0 is 0. So I'll go and put that guy in. Now actually what I'm going to do here is I'm going to do exactly what I did with the sine and cosine graphs, but this time I'm going to do it in radians and not degrees. So that's 0. I'm going to skip 2 spaces because that's going to be 15 degrees, or pi over 12 radians. The first guy is going to be pi over 6. The next guy is going to be pi over 4. And the last guy is going to be pi over 3. Skip another space, pi over 2. Skip another, 2 pi over 3. 3 pi over 4. 5 pi over 6. Skip 1, that becomes pi. So again, we're doing this super detailed graph right here. And it's just going to do this. And then that's 3 pi over 2, skip a space, 5 pi over 3, 7 pi over 4, 11 pi over 6, skip 2 more, 2 pi. Now, I promised you an explanation, and it won't apply to this one. Actually, it will apply to this one. It'll apply to this one in the sense that we still need to put down our 1 and our negative 1. So remember back in sine and cosine, I told you all to space out your 1 4 boxes. And I asked you to trust me, and I said I would explain later. Well, I'm going to ask you to trust me again and go out 4 boxes. 1, 2, 3, 4. That places you at pi over 3. Okay? Remember that. I'm going to go up 1, 2, 3, 4, and I'm going to call that guy 1, down 1, 2, 3, 4, and that's going to be negative 1. The reason why I had you go out 4 spaces to 60 degrees is because 60 degrees is pi over 3. And with pi being approximately 3.14, pi over 3 is approximately 1. That's why I had you space out your 60 degrees that way. So hopefully that makes sense now. And hopefully you're able to see the blue on the black when I wrote it down. So hopefully you're not in a room with glare. Okay, so let's go ahead and put down the pieces that we know. We know that tangent of 0 is 0. Now the other parts I'm going to identify are the undefines. The undefines should have a familiar graphical effect when you graph something that's undefined. We've seen this in logarithms. We've seen this in rational functions. That's going to be a vertical asymptote. It's going to be a vertical asymptote right there. Okay. Now, between 0 and pi over 2, I need a number that's really easy to plug in. In other words, its output is going to be really easy. Well, that's pi over 4. That gets me 1, so I'm going to put that guy up there. And what's going to happen is it's going to snake upwards and head towards that asymptote like that. Tangent of pi is 0, so I'm looking at between the undefines now. I'm looking at between these undefined regions. Tangent of pi is 0. 3 pi over 4 is my next known value because 3 pi over 4 gets me -1. So I'll go ahead and do that. And then tangent of pi is 0, we talked about that. And tangent of 5 pi over 4 is also 1. The way this grows is it's going to snake up like that. Just, this graph should almost look familiar. It almost looks like a cubic function. But it's not. It's not. It's asymptotic. And then the last little bit is 2 pi. That goes to 0. 7 pi over 4 is -1. And then that's going to arc down that way. And that is what your tangent looks like. I'll go and label him pi over 4, 1. The domain and range for this are going to be different. And so the range is actually going to be all real numbers. So I'm going to say the set of y such that y is an element of all real numbers. And why is that? Well, it's because the arrow shoots up and shoots down, meaning it goes way up and way down. The domain of this one is going to be the most different of any domain you've ever experienced. I'm going to start off with the set of x, such that x is all real numbers, because it's almost that, right? It's almost all real numbers. But it seems like I can't be at pi over 2 and at 3 pi over 2. Well, let's find out the distance between those guys. If I was to calculate the distance between pi over 2 and 3 pi over 2, that would be a distance of pi. And so that means that my next asymptote would be pi away also over at 5 pi over 2, and then 7 pi over 2, and then 9 pi over 2, and so on and so forth. So it seems like x can't be, so I'm going to say x cannot be pi over 2. And because there's a pi distance away every time, I'm going to say plus pi n, where n, and I'm going to define n is going to be an element, right? Just like this element right here. And I'm going to put down the letter z. Now this z here, what that means is that's math notation for integers. Integers are the numbers that are all whole numbers and their opposites. So that is the domain of tangent, where it's going to be any number it wants except pi over 2 plus pi n. So you're going to want to get used to that. Don't worry about that. That's just a squiggle. That's me closing off the bracket. That's nothing right there. So keep that domain in mind, because that one is the most that one is the weirdest domain you'll ever encounter, except for the other three that we'll see later. Let's talk about period. The period of tangent. Remember, period is when graphical behavior begins to repeat. So when do I see an x-intercept with the graph arcing upward while holding water? Well, it happens once at 0 and once at pi. It will happen again at 2 pi. So unlike sine and cosine, the period of tangent is a single pi. So hopefully that makes sense. That will wrap it up for tangent. So to summarize, we learned how to graph tangent, we learned how to find tangent using sine divided by cosine or y over x, and we learned about how to interact these coordinates from the unit circle in order to get our individual tangent values for graphing, and individual tangent values from the unit circle. So hopefully that all makes sense. Again, make sure you mind the domain. And as always, leave comments or questions in the comments area. I will see you all in the next episode.